Now let's look at how pulse width modulation works. But first we're going to look at a few critical details about how digital signals operate. We remember that digital signals have a high and a low value. Typically the low value is 0 volts and the high value is whatever the system is. It might be 1.7 volts, it might be 3.3 volts or 5 volts or even 12. Digital signals also have a rising edge and a falling edge. The rising edge is the transition from low to high, and the falling edge is the transition from high to low. Every regular digital signal has a period, and that is one cycle of a repeating pattern, and that is over some time, and this is measured in seconds typically. So digital signals have a lot of different properties, right? So we have the period of the digital signal, and we also have tau, and what tau is the what it does is it relates the duty cycle, or this is the ratio of the time on to the cycle time. So the on time of the signal, which is tau, what proportion of the signal is on to the overall time of the system. So a duty cycle is actually expressed as a percentage. It is a percent of the total period. So a duty cycle of 0.5, 50% is exactly half on and exactly half off. A duty cycle of 0.75 is 3/4 of the time it's on and 3/4 of the time it's off. A duty cycle of 0.25 is on a quarter at a time and off a quarter at a time. Now, let's think. Is there such a thing as a duty cycle of 0? What does that look like? A duty cycle of 0 is just a flat value. There is no on time, so it is always 0. What about a duty cycle of 1? What about a 100% duty cycle? What does that look like? A duty cycle of 100 or 1 is exactly a constant signal of high, so it never goes low. So here's a question. If I create a digital signal with a duty cycle of 0.5 and a frequency of 1,000 hertz or 100 hertz, then I change the duty cycle to 0.25. What is the new frequency of the signal? It's still 100 hertz. The duty cycle doesn't change the period, which is what defines the frequency. Remember that the frequency is independent of cycle time, right? So the frequency of 1 hertz is the same no matter if the duty cycle is 0.25 or 0.75 or a quarter or anything like that, right? And frequency is related to the period as the inverse. So frequency is the inverse of the period. So if the period changes, that's different. That's not the duty cycle. That's the time of the overall signal cycle. So if the period changes, then the frequency changes. But the duty cycle doesn't affect the period or the frequency. So the way we do this the way that we generate these signals in software or in most hardware systems is that we use a timer that does 2 events, right? So in the last video, we saw an event that happens at the end of a timer cycle right as it resets. A PWM generator uses a separate compare circuit to generate a new event somewhere in between the period part, the time where the timer resets. So in this case, what happens is we have a timer overflow, which defines the period. So we have a timer overflow here, which starts one new cycle, and we have a timer overflow here, which starts another cycle. So that defines the period. So the modulus register in our hardware is going to define the period of our PWM signal. Then we can also do a compare match, and we're going to use one of the channels of the timer to do the compare match. And it has its own comparator, and it'll post a new event that allows us to transition the signal from 1 to 0 somewhere during the period of the timer. And that allows us to do 2 events, one that resets or gives us a rising edge, and another one that gives us a falling edge and takes us back down to 0. So pulse width modulation is super handy. It can be a kind of digital to analog conversion, or it's used to control all kinds of stuff, right? And the idea here is that we're looking at the signal as the average voltage over time. So over a bunch of different cycles of the signal, if we average them, the duty cycle is basically an analog value of the total proportion of the signal. So my actual voltage is really the duty cycle times the difference between minimum and maximum of the overall signal. I get an analog value out, which is really cool. And I can step this as much as I want, as much resolution as I have to control the time on in my signal is how much control I have over the output voltage. What I can do with this is some pretty neat stuff. I can control the brightness of an LED, which I can control motor speed or rotation. So if it's a servo, I can control the position of a servo. If it's a motor, I can control how much power goes to the wheels of a robot and control its speed that way. Or I can even generate audio output. And this takes me back, because this Sony Discman here was the first CD player that I ever owned, and it had a little gold sticker on it right down here called 1-bit DAC, DAC. And basically what it is to generate audio, it generated a very fast PWM signal, then dumped it into a capacitor to smooth it out. And it would modulate the PWM signal to get rises and falls in voltage. And it did that fast enough, way faster than the 44 kilohertz we need to generate sound to make really high quality audio. And I love this thing. In high school, I would listen to this thing on the bus rides to school all the time, and I wore it out. I killed that Discman playing Smashing Pumpkins CDs and Metallica the whole ride to school. So our task is going to be a little bit simpler than translating CD audio. We're going to translate the voltage, use PWM to control the brightness of one of the LEDs on our board.